Okay, in this experiment we're going to be looking at the current produced by a coil in relation to the speed of the magnet that passes it. But first of all we're going to be looking at what happens when you charge a cap and how the current and voltage plays a part in the charging of a capacitor. Most of you will already know all this, but it seems for some it is hard to understand why I'm carrying out my tests the way we are. So basically we're going to be running a magnet past the coil. We're looking at my test bed. We'll go through that later on, and we're going to pass that magnet across that coil at different speeds and see if we get more or less current. So our peak current, the faster we pass the magnet across the coil, the peak current will rise, but the time duration of that current will diminish. In other words, it will be less than if we pass the coil over, or the magnet over the coil slowly. So basically what we got here is this meter here is reading the voltage across our capacitor. This is a super cap, so we can watch it happen slowly because we're dealing with very small capacitors in our test, but the same principles apply. This is our amp meter reading the current going into the cap, and our power supply up there. At the moment I have the current limit set to 100 milliamps and 6 volts of potential, because at the slower speed of our test the potential across our coil is 6 volts. So what we're going to do to start with is switch our power supply on, and we've limited the current to 100 milliamps thereabouts. Our meter will show a little more because my power supply meter is a little bit out, but not far, and we're going to watch the rate at which that cap is charged. So if I switch on the power supply now, you see we're doing very close to 100 milliamps, 101, and we can watch the voltage rise in that super cap. So at the moment, like I said, our potential is 6 volts, and of course the closer we get to that 6 volts there'll be a point where the current will drop right off, but it's only a 2.7 volt cap, so we won't be going up to 6 volts. You can see at the moment it's only 0.28 volts at 100 milliamps, and the reason for that is because we've limited the current. Our voltage on the output drops down. Now we can wind our potential voltage up any amount we like. It's now at 24 volts. We're still only delivering 102 milliamps to the cap, and it is still rising at the same rate regardless of the voltage. So back to 6 volts. What I will do is I'll show you that just for those that are learning. Once again, we can wind our potential voltage up to say 20 volts, and if we go back down and look at the meters, we'll see we still have 102 milliamps and the cap is still climbing at the same rate. So the only way we can get that cap to charge faster is not by increasing the voltage, but by increasing the current. So you can see the rate at which the voltage is climbing across the cap, about 0.01 of a volt every 3 seconds. If we go back to our power supply here and we raise the current up to say 5 or 600 milliamps, we now see that our cap is rising much faster. So in order to charge a capacitor, you can have all the voltage you like. It's the amount of current flowing into that cap that determines at what rate that cap charges and how much time it takes to do so. So very straightforward. In order to charge a capacitor quicker, we need to increase the current flowing into that cap. So what we're going to do now is we'll get rid of all this rubbish and we'll get on and have a look at our little DUT here, device under test, or our test setup, and we will run through everything we need to know about it. Okay, so here is our little test setup that I have made quite quickly. What we have here, underneath here, is a motor and gearbox from the windscreen wipers in your car. Attached to that, you'll see I have a nice large solid steel rod, 19mm. It's actually an old motorcycle front wheel axle. And on the end of that, we have a 19 by 25 N52 Neo magnet. Here we have a coil, it has a laminated steel core, and we are half-wave rectifying the signal coming from this coil, and we are using a Scotty diode so as we get a very low voltage drop across there, about 2.2 of a volt. So from there we go through over to our little chocky block here, and this is so we can put different value capacitors inside that chocky block. So in this case here we are using, our starting one here is, it's not going to focus, is it? And the light is pretty poor, but it is 220 UF, 220 UF. And our larger one is 470 UF, or microfarads. So the little chocky block here allows us to screw in and test each capacitor separately. Okay, so what else you'll see here is I have two strips or two brushes made from copper plate, and what happens is when our gizmo here spins, goes past the coil, induces an EMF across it, and the power is sent and stored into our capacitors. When this arm comes across, runs across these two brushes here, and it discharges the capacitor. So for every revolution or one complete cycle, the capacitor is charged and discharged, so as the next cycle is brand new and there is no charge left in the capacitor. So that's how this works. What we can do now, or what I will do, is I'll go ahead and wire it up. If you want to have a little look-see underneath, very simple. Just have our washing machine motor here and our two wires which will go into the power supply. We've just disconnected our switch in the gearbox, which would switch from forward to reverse, and of course you have your common ground. So at the moment we are directly wired to the motor, and we have only the forward direction power supply. So that is how our setup works. The magnet will pass the coil, charge the cap, and before the magnet passes the coil again, it discharges the cap simply by this steel rod here, shorting out our two terminals across the capacitor. We'll go ahead and wire it up, and we can have a little look and see how it works. Okay, so we're all set up. At the moment we're at 8 volts. We've wound our current back up. This motor only draws about 800 milliamps free running, and we have a limit of 5 amps, so more than enough power to do so. I'm not sure if you can see the very corner, I'm trying to get it all in, yes. So we have our little 220 UF cap in here at the moment, and we have our scope probe across that cap to measure the voltage. As you can see at the moment, there's no voltage in it, it is at 0. So when we start it up, you will see this machine rotating with this arm with a magnet on it past the coil. You will see the voltage jump up when it passes the coil, and then when it goes over our shorting brushes here, you will see it drop back down to 0. And like I said, this is so every time you complete one revolution, it is one single cycle, and this allows us to freeze our scope, measure the voltage across that capacitor. We then can calculate the stored energy, and you could also calculate the amount of current it took to charge that capacitor to that value. So we'll have a look at it running. We're then going to disconnect the cap, and then we're going to place our scope across the AC side of our coil, or just across the coil before the little diode there. And what we're going to do is have a look and see at this speed that our 8 volts causes us to rotate, we're going to see what our potential voltage is. And when we're looking at that, we'll be looking at the top half of the waveform as the magnet passes, because that is the direction we have our diode in, and it is that top half of the waveform is what will be being sent to our capacitor. So I'll switch it on, and you can see when it passes the coil, the voltage drops up, goes over our brushes, and the capacitor is shorted or discharged, and we start from 0 volts again. So the coil passes, voltage goes up, shorts out, voltage drops to 0. So every time we complete a cycle, we'll be able to freeze our scope like so. Switch this off. You can see at the moment we have our maximum was 2.72 volts, minimum was 2.64, our average is 2.68. So very easy to calculate the energy that was sent from that coil into this capacitor. Alright, so of course we'll be doing 5 freeze measurements and writing down the values of each one. We can average it all out, but every cycle is going to be extremely close. The distance between our magnet and our coil is not going to change. That's of course fixed throughout the whole test, and once we've taken out 5 averages, we're then going to remove this here little cap and put our larger one in, and we'll see what voltage we get across that. We're then going to speed up the machine so our magnet passes the coil faster, and have a look and see if we can raise the voltage up to the same level as our small cap in this large cap. So of course we know if we pass the magnet past the coil faster, it will produce a higher value current, but the time that that current is being delivered to the cap is much smaller than when this is passing slowly. So we're looking at about 2.5 volts across our cap, so now we've got to go and make sure that we have more than that across our coil, because as we know, as the cap is being charged and gets closer to the supply voltage, the current will drop off. So we want to keep this voltage across our cap at least half of what is available from the coil. So I'll go ahead, disconnect the cap, hook the scope up to the coil, and we'll come back and see what we got. Okay, so we now have our cap removed and we have our scope across our coil before the diode. And now the reason it looks like this is because we have our time durations right up at 1 second per division, because it is a very slow rotating machine. Well, what we're interested in is the top half of the wave, and we zoom in there like so, you'll see our Vmax is around 6 volts. You can probably see the little line going through there. Yes, you can see it changing. That Vmax is what we're interested in. So we've got very close to 6 volts of potential when we are sending the current or the power to the capacitor, and we're only good charging to about 2.5 volts. So our voltage potential is more than adequate to do the job. Right, so we're going to go and get set up now, and we're going to start our testing and see how we go. Okay, so we're right to do our first half of the test, and that is with the 220 UF cap in place. Our scope is ready to go. We're set on 8 volts, our power supply, which will give us a nice steady and even speed past that coil with our magnet. And of course, as we know, the energy in the cap is dissipated or removed when we short the cap via this steel arm running across our 2 copper brushes. So what we're going to do is let this machine run, and once our voltage jumps up on our scope, we will freeze it, and we're simply going to do 5 tests or 5 captures where we're going to freeze the scope 5 times, and we're going to write down the voltage across our cap, and this way we can get an average voltage across our cap, which will give us an average power or an average energy value held within that cap. And then what we're going to do is we're going to remove our 220 UF cap, replace it with our larger 470 UF cap, and we're then going to run the same test, but we're going to raise the speed at which the magnet is passing the coil. So as we've seen at the start of this video, regardless of the voltage, it is the current that allows that cap to be charged quicker. So what we're up against is, once we speed up our little device here so the magnet passes the coil quicker, we will indeed get a higher peak current value, but the time duration in which that current is flowing into our cap is going to be much shorter. So rumour has it that regardless of how fast you pass the magnet past the coil, the total average current will always remain the same. And this arised from a question that was asked: do you not get more current when you pass the magnet past the coil quicker? So, well, the answer is you get a higher peak current but a shorter time duration, and we want to find out if the overall current per cycle is higher or lower if we pass the magnet across the coil quicker. So that's what we're going to do. We're going to start our test now. I can freeze our scope. We can now write down the measurements. I'll zoom in on the scope now. Might be just easy if I carry it forward here. And we're going to take down the average value of each test. Don't you hate autofocus cameras? Okay, so our average voltage was 2.84 volts on that run. Start our scope again. Do another capture. Once again our average voltage is 2.84, and of course it should remain quite constant because the speed is constant. Like I said, that is a very heavy bit of metal to keep the inertia up as the magnet goes past our steel core. There may be a little tiny variation in speed, but it will be pretty constant. Freeze it again. Once again our average voltage is 2.84. I think we're going to find that it's going to be very steady throughout the test. We of course do have our maximum voltage there, 2.88, an RMS value, and I do have a minimum value over there too that you can't quite see, which is 2.8 volts. So average is doing pretty well for us. Zoom out a bit there so you can actually see that it is resetting every time. Stop. Once again 2.84. Once again 2.84. Okay, so now we're going to go and change the value of the cap, run our test again. Okay, so we're ready to do the second part of our test. We've taken our little 220 UF cap out. We have our 470 UF cap in. We'll reduce this to the same speed to start with, and then we're going to double the speed and see what we got. But we'll have a look at the voltage across our 470 UF cap at the same speed we were running the last test on. One thing I forgot to mention was we've seen the open voltage of our coil was very close to 6 volts on the forward voltage peak, which is what we are using as far as the direction of the diode goes, but the voltage across the coil is of course clamped by the voltage across our cap, plus the 0.2 to 0.3 volts drop across our little Scotty diode there. So we know the voltage of the coil is relatively the same as the cap, plus that 0.2, 0.3 volts. So our coil voltage in the last test was going to be around about 2.9 volts. In this test here, coil voltage is going to be actually lower, and because our magnet is now passing the coil faster, about double the speed, the time period of our current being generated is half. So we'll start her up now. Reset our scope here, and as you can see, the coil is not discharged at the moment. It is now, and make sure I might just turn that up a little bit, so make sure that they're getting good contact, and the coil's being discharged properly, which we can see on the scope anyway. Alright, so let's start this thing up. We now have our 470 UF cap in, and we're going to do the same again, 5 shots of the voltage across our cap per cycle, and we'll see how we go and what we end up with. So at the moment we're running at the same speed, we're on our 8 volts. Have a look at the voltage. I'll move this in closer again so you can see it. There's a scope there. We've got a cord problem down here. About 1.8 volts going into that cap, or into our larger cap. So yes, about 1.8. In our test with our smaller cap we had 2.84. So some of you might be doing the calculations here at the moment and working out how close it is. Even with this larger cap put in place and the speed kept the same, the energy stored is going to be a little bit greater. And there's a reason for that. We're not going to get into it in this video. We're going to see if we can nut it out. And it seems that those in the know are missing this point altogether, regarding the magnetic field being produced by the coil and what effect it has against the magnetic field of our permanent magnet. But like I said, we'll leave that to the next video. Alright, so what we're going to do now is crank up our speed. Okay, so at the moment, I've checked the RPM. We are now, we'll zoom out a bit, running at twice the speed. 20 volts gives me very close to twice the speed. Okay. So our current value would have gone up, but our time period has been halved. So it now gets a bit tricky, this speed, to catch the scope while the voltage is across our, zoom in there a bit, while the voltage is across our cap before it gets discharged. But you can see every cycle it is discharged and then recharged. Okay, so there we have 2.2 volts. Now I've lost the pin, I think I just put it inside. And I don't know if I've got another one in the drawer, just going to move you here a bit so I can see in the drawer. About 4 in here, I don't know if any can work. Doesn't. That one does. Okay, 2.2 volts. And like I said, speed is very constant. Our voltages should be near exactly same because the magnet passes the coil at the same speed every time. So quite an accurate test bench we got here. Once again 2.2 volts, and I think we're going to find it's going to be the same all the way through. .2 volts. Now remember, we're going on the average here. Maximum voltage 2.4, minimum is 2.08, because you can see these little spikes here, and that is just noise from the motor. Okay, so once again 2.2, so we're going to be pretty much the same all the way through. Excuse me. 2.2. I am on 2 volts per division as well, by the way, and we have been throughout the test. 2.2. Peak voltage there, or maximum voltage is 2.48, but like I said, that's those tiny little interruptions you can see there. So there's no need to average any of that out, because in both tests the voltages were identical throughout, so there's nothing left to average. So in test 1 we had 2.84 volts across our little 220 UF cap. So that gives us a charge of 624.8 microcoulombs and 887.2 microjoules. And that one there. That was with the magnet passing the coil slowly, of course. Now we switched up to our 470 UF cap. I can zoom you out again now. We switched up to our 470 UF cap from our little 220 UF cap, and as you just seen, the results were 2.2 volts for all 5 captures. So that gives us an energy value in the cap where our charge or our joules is 1.137 millijoules and a charge of 1.034 millicoulombs. So we know now that the coil, because we had a lower voltage across this larger cap, our coil's peak voltage was also lower. But we know even at the slow speed it was capable of delivering 6 volts, so our potential was definitely high enough in the first test. Now the peak voltage in this test, where it is going faster across the coil, of course, would be a lot more. But once again the coil is clamped at the 2.2 volts in this half of the test, plus 0.2 or 0.3 volts diode drop. So what does that leave us? How were we able to get more charge in the larger cap than the smaller cap in a shorter period of time, because our rotor is spinning faster and the magnet is passing the coil faster? And the only answer to that is, as we've seen in the very start of this video, when we were charging that super cap, the only way you can charge a cap faster is by increasing the current. So I think it's very plain to see that the faster we move a magnet across the coil, the more the average current value works out to be, unless someone can see a mistake I've made in this test. But like I said, 220 UF cap charged to 2.84 volts with our slow pass. That gives us a longer time duration but a lower value of current. And the 470 UF cap charged to 2.2 volts, a shorter time duration because the magnet was going past the coil faster but a higher current peak value, and it would seem that the average value from both tests indicate, or the average value of current flow from both tests indicate, that the faster we pass a magnet past the coil, the higher the current value delivered from that coil. Okay, so now I'm going to put all this video together, and in the next video we're going to have a look at peak currents, because apparently the peak current doesn't change regardless of how fast you move the magnet across the coil. So I've been told, and I have a feeling that is wrong also. Alright, thanks for watching, hope this was helpful, and we'll see you next video.